Okay, basically what we want to do is we want to create a cheap drone swarm. Now hear me out. When I say this, I mean this in a very unique um, way. So basically, how do I describe this? So for a certain given use case, let's say search and rescue, right? We have, let me just the rectangle tool actually. We have a map and we have obstacles and stuff like that, blah blah blah, whatever it is. And then we have some target destination and target destination, and we have, a starting point, right? So essentially, the classic thing one would do to get from the starting point to the destination is run Dijkstra's or some other pathfinding algorithm, right? Um, to get there. So that you can do that. I don't want to review 2SI, 3SH anymore. You can look into that, whatever. But essentially, what we want to do is we want to create. So I mentioned before, we wanted to make create a cheap drone swarm that can do this kind of stuff. Essentially, sorry, the cars were loud. But we want to create one like that can essentially not only have a better understanding of surroundings and be better at search and rescue, but is also quite cheap and therefore scalable and actually can be used by people that aren't the U.S. government. So the way we're thinking is we have one hub, right? We have a hub here that'll do all the computations for these drones. The drones themselves, they're all going to be very cheap. They're going to be not cheap, but like we'll be able to minimize the cost per drone. So this way, when we actually try to build this form, it's not going to like break the bank. And not just that, each drone is going to be a different type. So there's two different types of drones. One is the mapper. So this is the drone that is more advanced than the others. This one will actually have a stereo depth camera. So we were thinking, first of all, was to actually map the area. We're not using LiDAR. So LiDAR is not happening, right? We're going to use stereo cameras. And hear me out. We'll get to why that's ideal. I mean, first off, it's cheaper, right? And then we're also going to be having, so we're going to have approximately 2 to 3 mapper drones. Then we're going to have a scout drone, right? Scout drones are going to be either cameras or they're going to be sensors. Like or sorry, radars, depending on what we need. Any kind of sensor, but like these ones are like the very lightweight, like cheap ones we want to use. And then the third one we're gonna have is like a payload or like a guidance one, or more like we could think of it as like a motherboard. We're gonna have one of these. And we're thinking of having around 6 to 8 of these ones. And essentially, this is the main brunt of it. And we're gonna, as we scale with the scouts, we're gonna need more mappers, and we might need more payloads. I don't know. We're not really sure about that yet, but essentially, kind of describe the stages that our system's gonna go through. If I could just make more space for myself here. Yeah, perfect. Right. So essentially, it's gonna have 5 stages. So we have 5 stages. Stage one is perception or vision. However you want to see the outside world. Right. So real quick check if I'm still recording. Looks good. Okay, so perception. Perception is the first stage. So each drone has each drone makes a local map. So I'm just gonna put down local map. Local map for each drone. Local map, each drone. Each drone. Right? And it uses the bird's eye view algorithm. So basically any all the 3D spaces it maps becomes 2D or 2.5D. I'm not really sure if it's 2.5D or 2D, but yeah, that's what it's gonna do. And this will just kind of let us um well, we could also use cross-modal attention as well. So that plus cross-modal attention. So we'll be able to allow us to, I think this is probably the most important part because having cross-modal attention will actually allow us to reduce the hardware costs, um, or not the hardware costs, but the complexity quite a bit. So cross-modal attention. For SID, that basically means that the information that we get from vision can actually influence how we move or move our position. That's basically what cross modal means through multiple different ones. So to expand out, so that's the first stage. We want to get have a way to actually take in our surroundings. Stage number two, that is, so this is a little bit of the complicated part, but we want to be able to fuse all the local maps together. So I can call this stage fusion, right? And all of the local maps are fused together, right? And they make a global map. So we're going to solve this like global map, right? Global map, right? Make a global map at, and this is going to be located at the hub over here. So global map at the hub, okay? And what else? This one, I'm not really sure how often we should update it. I feel like we should update it quite often. So basically, as we get the data, we'll update the global map as each of the local maps are compiled. Um, yeah, that's basically the issue. We get all this data from all the different drones. They have their own local maps. Obviously, we have to account for the fact that some might not be as accurate as others. Like, for example, the Scout is not going to be as accurate as the Mapper, and the payload might have the most expensive gear. We'll have to see. But basically, we'll be able to have a bunch of different sources of information across this area, right? So that's stage two, is combining all those things together. All right. So stage three, this is the more of the ML focus. This is where EX would kind of thing. But the way this works is this is what we call the stage search. Okay. So search, right? So basically, what we're thinking is we're creating some kind of learned model, and we have different stages for this, and I'll elaborate on that in a moment. But um, it's learned models, and basically what we do here is give me just a moment to wrong thing. Okay, it's fine. Um, okay, it's fine. So stage three is going to be about a couple of different stages. So we set up a couple goals for this because this might be the hardest part. So I'll put a start here. So our ideal minimum viable product is to have something that works with a Hungarian model. Basically, we run a um, brute force approach um, on all the best possible combinations of drones and positions and where they should go based on where the other drones are, and we choose the best one. Right? So Hungarian. That's called the Hungarian algorithm. The second one um, was I think it was also using more attention stuff. I kind of forgot what the second one was, but the third one I remember is using multi-agent systems. This is this acronym. I forgot what it stands for. If I want to know more about this, but this is like our third goal. This is like best possible case, but this could still work with Hungarian. It might be a little more computer tested, but if we can get it working with Maple, that'd be really, really nice. Right. So that's fine. And then number four. So stage number four is um okay, I guess when we find a target. So we find a target of, or this is actually I guess you can call it the pathfinding or path, stage four is pathfinding, right? So searching is to find the best path, and then pathfinding is actually like going through like following the actual path. So I guess path planning is a better, path planning sounds better for what it needs to do, right? So basically, once we've actually found the correct target based on stage three, we can go ahead and say, okay, now we can we have to find the safest route, and safe, again, is determined by multiple things, not just, distance and all that, but rather this is where we kind of want to make sure we have cross-modal attention working because we want to make sure if there are any visual hazards, can we first off need to identify that the visual models are in fact, bad. Some visual parts are, some visual things that we see are hazards and some aren't. And so, um, yeah, essentially we want to be able to take that into consideration when we're actually planning our routes. And so we compute the safest route using D sharp, right? And we basically see, okay, this part was kind of hard to explain. I kind of didn't understand as much when I was explaining it, but essentially he said we wanted to replan things cheaply. So I guess you could say cheap replanning, right? Cheap replanning. Okay, that's cheap replanning. Whenever we actually see new hazards. So cheap replanning when new hazards appear. I don't know what he meant by cheap, but hazards, right? Cheap replanning. Okay, so that's that part explained. And then the final stage, right? Final stage is stage five, where essentially we actually do this stuff. So I guess we do execution. This is like when it actually happens, right? So we spent all this time planning and seeing how to do things best. So remember, we got all the information we could. we have each drone locally mapped. The mappers use the stereo cameras, um, and scouts use the camera, the radars, or whatever they're equipped with. But they're there's a ton of them, and they're very cheap, so we can get a lot of different images. Um, in SLAM, obviously, to render the local environment and everything, because it's all mostly going to be embedded, and to actually work with it, right? Then we put them together, we fuse them together to make a global map, right? Accounting for the errors that we might encounter in the scout versus, like, I'll probably weigh the ones for the mapper and the payload higher than that of scout, but again, still it does help out a little bit as well. Then we search for the best possible, um, I guess you could say orientation or arrangement of these drones, which drones should go to where based on what we're seeing. And then number four is actually planning our path to the area of interest. In this case, it could be here, right? So yeah, we use G-sharp light, and whenever new hazards appear, and let's say a scout spots a hazard, and it obviously updates our global map, then we can easily recalculate and figure out, alternative routes that would benefit us, because we're not just doing like a basic pathfinding out. Like, we're actually considering that we have real life hazards at play. Oh boy, my thing. I guess the thing ran out of memory. Okay, that's fine. Um, we're actually considering that real life hazards are there, and we can actually like think, sort of kind of think like how someone in an emergency thing would. And execution again is actually doing the job. So what this works is that the hub assigns responsibilities. So uh, hub gives out instructions or responsibilities um, to each of the drones, and the drones again in turn they give back the data, like the sensor data and all that stuff, um, to the hub, and that basically allows us to go back to stage one, see if we need to make any changes to our thing. So to break down stage three, back to what we were saying here. So our first goal, like minimum viable product, right? Minimum viable product, is to use Hungarian. And so Hungarian, basically how that works is we have, like, it's not really a huge network, but like basically have basically have a small network that can compute every combination of where the drones are, every drone, and where it's the most optimal place for them to go. So it will kind of run a brute force algorithm and see which one's the best, and then see and get all of them, and the Hungarian chooses which one is the most optimal and best. Um, and this is like the most like reliable result. Like, I don't want to end up here, but in the worst case, this might be our final product. It will still work. Obviously not as well as we want. Um, and so what that kind of looks like is when it's actually running the analysis is that it's going to see, okay, um, let's score how useful it is to send a drone to that area. Like, for example, is it better to send a scout drone to that area that's more cluttered? So like it's better allocation of where things should go. Um, and again, this would be quite useful in like actually reallocating resources. Um, Based on what we're seeing in like a scenario like this. Um, and yeah, we also calculate the hazard or the weight of each route, right? Um, and that's again determined by not only just distance, but also obstacles, dangers, and all that sort of thing we're seeing. So we're gonna have multiple streams of attention, but in general, that's kind of how it works. That's factored into the cost, and we kind of choose the best combination these of drones and where they should go, right? So tier number two, I didn't mention this earlier, but basically how tier number two works is that we add attention layers or more attention layers, um, one more attention layer actually of the drones to each other. So we already have vision and we already have distance of each other, right? But what about, can we also have one more attention layer? So also attention layer of drones to drones to each other. And what this kind of means is, let me just write this down. Drones to each other. And basically, um, what this means is that we're kind of each of the drones kind of aware of each other when making decisions, and when in doing so, it kind of creates a new model where of behavior that I feel like is more well informed, because right now it kind of does the star formation, right? It communicates with the hub and all the other drones. But with this, maybe we could have um, some kind of peer-to-peer network also working as well. This might be very expensive though, but or there might be a really smart way to do it still using star topology. We'll have to see, right? But that is number two, and then number three, obviously, um, is where we use reinforcement learning, um, and that is with MAPO. So MAPO actually stands for multi-agent proximal policy optimization. Wow, what a mouthful, right? So, of course, with RL, you kind of fuck around and find out. So basically, how that's going to work is that you're going to basically discover how they can work the best possible way. So it's going to take a lot of training. That's the problem. We do have a guide we can use for compute, but basically discover how things work rather than like trying to orchestrate everything on our own way. And again, to reiterate, um, how everything works, no LiDAR. We don't want to use it. It's too expensive, right? Like a basic LiDAR camera will cost you like what, $200? It's nuts, right? If you want to make something scalable, we cannot rely on that. And so keep our costs down. And of course, most of the time we're gonna see a star hub, like the hub is like a star network, right? We're also gonna see that. And what else? We might consider drone-to-drone networks, like peer-to-peer networks, as mentioned here. And we're gonna probably simulate this a lot before we actually start flying stuff. Um, or we'll probably try with small subsets of each before we actually make the whole investment. I feel like that's fair. And if we ship these tiers, but this project in tiers, but this part's probably the hardest to work with, um, because it's basically the whole brain of the algorithm, right? Like actually figuring out how to allocate things and actually make things work. So this is like the brain of the algorithm. So having three different milestones for it would work, even though the first milestone would work, it can definitely get better with more information. And yeah, that's basically it. Hope it makes sense. We do appreciate feedback. We haven't spent too much time on this one, on this idea, but I think it's really unique application, and I really feel like um, we can have a lot to show for it, and it really targets a lot of boxes as well. A lot of ML stuff to do. Um, Distributed ML. I'm still not sure what you mean by that yet, but I feel like we can definitely target that, especially with your feedback. SID, we're probably going to be building. We'll SID in everybody. Everyone's going to have to contribute, unfortunately. But uh, not to the hardware part, but in general, you'll be probably doing a little bit more than you expect. But um, we're probably going to get like cheapest possible drones that can fly and then build the modules ourselves. So it's gonna be a lot of DIY. So we're gonna have a lot of fun making PCB boards um, and well, actually making the drivers and everything for these to actually coordinate the behaviors that we want. So it's gonna be very fun, very fun. I think it would be a good combination of hardware and software, and of course ML. And the hub is, I think, will be probably the most unique part is figuring out how it can actually manage these competitions, um, and while also being portable and hopefully affordable because again we are spending a bit of a budget on the mapper and the scout and the payload. The payload drone, by the way, this is one idea that we had was that like for example, if we're trying to put out fires, and I don't really know if this is a very viable scenario to have drones in, but the payload drone could carry water and it could load up each of the scout drones, which would or at the very least it could like or load up each of the mapper drones because the mapper drones are probably much stronger than the scout drones, um, which will usually carry empty tanks at first. I'm not really sure how that'll go out, but basically we have this payload kind of serving as uh, it obviously communicates with the help for the rest based on how the global maps are generated. But um, yeah, like that would be a possible application of a payload drone. I didn't elaborate on that enough. But for example, carrying water, um, or fire extinguisher, like what do you call it? Solution, right? The fucking foam, right? So that's something that I thought would be kind of interesting. So yeah, let me know if you have any questions and peace.